/blocked, please click on the play button on the media player. For those of you who want to know if the session will be archived, the answer is yes. It will be archived and will be available for review within about 24 hours. Once the archived webinar is available, a notification email will be sent to all the registrants. We encourage questions, and I hope we have time for several, which we'll take at the end of our presentations. As your questions occur, please type them in the box provided on your computer screen on the right-hand side, I believe, and hit the submit button. You don't have to wait until the end of the presentation to begin submitting questions. If you're looking for the PDH certificate code, this will be given in a slide at the end of the presentation. As you look over your screen, you should also see buttons that allow you to enlarge the slides if you so desire. About volume control, if you're listening to the audio portion of this event over your computer speakers and you need to adjust the volume, you may need to adjust the master volume on your computer. At the bottom of the slide in front of you are a couple of additional widgets that will improve your viewing experience, including a green resource page to the far right with today's presentations. Now, I would like to introduce our presenters for today. We have Kyle Koppenhafer of Altisim Technologies. Kyle has been one of the principals and leaders at Altisim Technologies for 15 years. He works with customers to identify how computational analysis can be used to further develop their products and manufacturing processes. And prior to co-founding Altisim, Kyle worked for the Department of Defense and the Edison Welding Institute. He holds a PhD in civil engineering from the University of Illinois. We also have with us from Altisim Joshua Thomas. Josh has over 8 years of computational analysis experience, including graduate-level training in computational mechanics modeling. At Altisim, he plays a vital role in developing solutions to a wide range of multiphysics problems using Comsol multiphysics for the aerospace, petrochemical, medical products, and consumer products industries. And we also have with us today Chandan Kumar of Comsol. Chandan is an applications engineer specializing in structural mechanics and the analysis and design of micro-electromechanical systems. He joined Comsol in 2009. He earned his PhD from Penn State University, where he studied the dynamics of the self-assembly of semiconductor quantum dots. He is a senior member of the IEEE. For today's agenda, we will start off by looking at the piezoelectric thermal structural modeling. There will be a live demo. We will go after that into a Q&A period. And then at the end, be sure to save it for the end, we have different options for you to go to events where you can try Comsol multiphysics. And with that, I'm going to go into our first poll question, our first and only, I should say. This question, please choose one of the options and hit submit. Don't chat back your answer because that will not be tallied. So the way to do it is to click one of the options and hit submit. And the question is, how does your organization use computational modeling? And select all that apply. So you don't have to choose just one. Check all of them that apply to you. So extensively by internal staff, it is relied upon for technology development. Frequently by internal staff, it's not the primary driver for technology development. Infrequently by internal staff, frequently by external organizations, and infrequently by external organizations. So those are the 5 options we have. Select all that apply, and I'm going to go ahead and push out the results. And with that, I will hand it over to Kyle. If you have any thoughts about some of the results of this poll, feel free to share or just begin your presentation, as you like, Kyle.
Well, it's great to see that almost half the people here today are using computational analysis extensively. That's really wonderful to see. In a population of engineers, 50% is not a typical number. So it's great to see that. Alrighty, so let's go ahead and move into my part of the presentation. And I wanted to thank you for taking your time to listen to what we have to say about this, what we consider to be an important topic. By watching a demonstration of how Altasim develops complex multiphysics models for our clients, you're going to learn more about the software and how to use it in product development cases. Analyzing products constructed with piezoelectric materials is another example of the application of the quote that's often attributed to Albert Einstein, which is, "Everything should be made as simple as possible, but not simpler." With piezoelectric materials, the second half of that quote can be very important. The analysis should not be oversimplified. As such, designing with piezoelectric materials represents a significant challenge to engineers due to the multiphysics and anisotropic nature of these materials. Engineers need the knowledge of how to analyze these materials and powerful multiphysics software with which to conduct the analyses. Whether the design is a microphone or an igniter for a camp stove or a surgical scalpel, a solid knowledge and powerful analysis tools will improve the design. By watching our demonstration of how Altasim develops complex multiphysics models for our clients, you're going to learn more about using the software for actual product development cases. We would use the complex problem of the heating of a vibrating structure driven by a piezoelectric transducers as the case study. We solved this case of this class of problems for our clients using Comsol multiphysics to represent all important physics in the problem. This example is one of many where we have supported technology development of our clients by developing models using Comsol multiphysics. We offer a wide range of services to support computational simulations of product development. To provide an overview of how the physics of this problem couple together, this slide shows the relationship. The driving physics for the entire problem is electrostatics. An AC voltage is applied to the piezoelectric material to produce a shape change in that material. This vibration produces an overall vibration of the structure. The material being vibrated will damp some of that vibration, and this energy loss produces heating. The heat source then drives a heat transfer problem that accounts for the conduction through the product and convection from the product surfaces. Heating of the material produces thermal expansion and perturbs the structural vibration. Temperature-dependent material properties are not included in this particular analysis, but they could be included, and that would provide an additional coupling back to the piezoelectric materials and the structural vibrations. So virtual prototyping is extremely helpful for designing piezoelectric devices. Piezoelectrics are a very special class of materials, and they're used in a wide range of products. I mentioned, camp stoves would be a very simple example, whereas minimally invasive surgical devices would be a much more complex example. But in all these examples, the material itself is rather complex. There's a multiphysics response, and the designers can be greatly assisted by advanced design tools like virtual prototyping. For those that are new to piezoelectric materials, I'd like to spend a couple minutes to talk about their application and then get into some more specifics about the material itself. Piezoelectric devices interact with many different physics to increase the multiphysics nature of the problems. They are often used in fluid control systems for highly precise controls. The acoustics industry uses piezoelectrics extensively in both the direct and the inverse effects, and I'll talk more about those here in a couple minutes. And they do that by converting acoustic waves into electrical signals and electrical signals into acoustic waves. Often, piezoelectric material is included in a larger control circuit where the differential equations that drive that control circuit also need to be included in the analysis. So let's start diving into some of the details, and we'll start specifically with the piezoelectric materials. This special class of materials transfers energy between the electrical and mechanical states. Piezoelectric materials are materials that can produce electricity due to mechanical stress, such as compression. These materials can also deform when a voltage or electricity is applied. The typical piezoceramic materials are non-conductive ceramics or crystals that are placed between two metal sheets. For piezoelectricity to be generated, it needs the material to be compressed or squeezed. Mechanical stress applied to the piezoceramic materials then generates electricity. The piezoelectric effect can be reversed, which is referred to as the inverse piezo effect. This is created by applying. For piezoelectric materials, Mechanical and electrical responses are coupled via the constitutive equations. In the stress charge format, the stress T is related to the strain S and the electric field E, while the electric charge density displacement D is related to the strain and electric field. The stress charge form of these equations represents a popular constitutive model. Another popular formulation is the strain charge equations. Typically, the user will decide between these two forms of the constitutive equations based on the material properties available. During our demo, we will use the stress charge form, but both forms are available within Comsol multiphysics. In addition, most multiphysics problems, in addition to these multiphysics problems, you also have an aspect of the anisotropy of these materials. As you see, when you look at the stiffness coefficients and the electrical permittivity, these are matrix quantities, and as such, can represent anisotropic material. So where does that anisotropy come from? Well, piezoelectric materials go through a polarization process prior to use. This process takes the microscopic electric dipoles, which are randomly oriented, and aligns them in a single direction. And they do this typically using either a mechanical force or an electric field. And once the poling process is complete, the dipoles remain in the poling direction. And this poling leads directly to the anisotropy in the mechanical and the electrical coupling. This poling direction is critically important to defining the material properties, and often the poling direction does not align with the global coordinate system of the model. Thus, a user-defined coordinate system can be used to specify the poling directions. And my colleague Josh Thomas will show this important feature during the construction of the demonstration model. Now, since all piezoelectric problems are inherently multiphysics, the boundary conditions for these models must include electrical and structural constraints both. Without these sufficient boundary conditions in both physics, the finite element solution can be meaningless. So let's go ahead and move into the structural side of this problem. So materials typically damp structural vibrations such that additional energy needs to be added to the system to keep the structure vibrating. This damping is produced by material losses in the material, and these losses are typically manifested by the heating of the vibrating structure. Thus, to include this effect, there needs to be a heat source associated with the material loss included in the model. This temperature change can influence the solution. When a material heats, it goes through thermal expansion. If the material is unconstrained, then it will expand freely into a larger shape like you see on this slide. Any constraint of the material will reduce the thermal expansion, but it does introduce a thermal stress in that process. For a structure that changes shape due to thermal expansion, the natural frequency of the structure will change. This change is typically small, but can play a role in the performance of the device. In addition, constraint of the thermal expansion of the piezoelectric materials introduces additional stress that can change the response of these materials. The demonstration that we're going to show today is going to focus on a medical device. The harmonic scalpel is a surgical instrument used to simultaneously cut and cauterize. Unlike electrosurgery, the harmonic scalpel uses vibrations instead of electrical current to cut and cauterize the tissue. There are several issues that we sought to address in this design. One was to minimize the heating of the hand unit so that the surgeon could hold it comfortably. Another was to include the effect of heating on the vibrational response of the device. This includes the shape change and the additional stress on the piezoelectric materials. To solve this problem effectively, an anisotropic formulation was applied. This assumed that there are no changes in the geometry or boundary conditions as you move circumferentially around the device. A stack of 4 disks of piezoelectric material drives the vibration. The 3 primary physics considered in this analysis are the structural mechanics, which includes the piezoelectrics, electrostatic excitation of the piezoelectrics, and the heat transfer due to the vibrational heating. And then you're also going to need to be able to couple between those different physics. So the piezoelectric materials are contained within the structural mechanics. Thus, the material properties and pulling directions are specified in this section. Sorry, I've lost a slide here. Okay, here we go. Okay, so the slide we're looking at here is looking at the boundary conditions for the structural mechanics. The axisymmetric formulation enables us to represent the model as a single radial slice of the device, which you're seeing in the image here. The axis of rotation is shown as the red vertical line, and that axis of rotation constrains the radial direction. So we don't need to worry about adding any additional radial constraints to the problem. The only other constraint that we need to worry about adding is a constraint in the vertical direction. And once we've constrained that, we now have fully constrained the problem. Okay, now on to the piezoelectric materials. The piezoelectric materials are contained within the structural mechanics module. Thus, the material properties and pulling direction are specified in this section. The stack of 4 crystals is pulled in alternating directions, as you can see on the slide here. And a user-defined coordinate system will be used to specify the pulling direction. So moving on to the electrostatics. The electrostatics of this problem are relatively straightforward. A voltage is applied at the electrodes between the stack layers, producing a mechanical movement of the material. Each crystal has one electrode grounded and the other electrode has a voltage applied. And now let's take a look at the heat transfer part of the problem. The thermal conductivity of the material is defined and then can directly calculate the outer surface of the device then needs to be specified as a boundary condition. Without a convective flux, the device could not reach a steady state temperature. So with each of these primary physics defined, the coupling now needs to be specified. Piezoelectric material response needs to be coupled to the applied electric fields for the electrostatic solution. And this coupling will cause deformation of the piezoelectric material. The second multiphysics coupling couples the vibration into the heating. Comsol multiphysics has the ability to calculate heating due to structural damping of vibrating material. And Josh Thomas will show this coupling in his live demonstration. So with that, what I'd like to do is go ahead and transition this over to Josh so he can show you guys how this problem is set up in Comsol.
Great, thanks, Kyle. You did a great job of laying out the framework for what I'm going to do right now. So I'm going to actually build this model from scratch. I'm using Comsol multiphysics. So this is the opening screen that you get in Comsol. And I'm going to begin building this model using the model wizard. It's going to be a 2D axisymmetric model, Kyle described. And we're going to add in the physics interface here called piezoelectric devices. And this is going to provide us with both the solid mechanics equations as well as the electrostatics equations. And in addition, it's going to provide us the coupling between those two sets of equations. The study type that we're going to start with is eigenfrequency analysis. I'm going to import this two-dimensional geometry from File. Browse for that. And so here's our structure with the axisymmetry axis in red. So remember, this geometry is revolved 360 degrees to get the full system. The next thing that I'm going to do is set up the piezoelectric material domains here. So by default, Comsol assumes that all domains are this piezoelectric crystal, but that's not the fully, we haven't fully defined just the linear elastic domain. So only a few of these domains are actually the PZT crystals. So what I'm going to do is clear out the selection list, and then the only domains that are PZT crystals are these 4 domains right here. Now I'm going to only add this one, and then this one and this one actually I'm going to add with a separate material definition because of the polling is going to be reversed. And Cal mentioned the importance of having the separate pollings. So this one here, you can see in the settings, has the coordinate system and the polling direction defined by this default coordinate system. Now, if you go under definitions here, you can see that there are a number of predefined orthogonal coordinate systems that have the polling in different directions. If you did have a polling direction that was not aligned with one of the axes in your problem, you can create your own custom rotated system using Euler angles to define any orientation that you need. So for us, I'm going to add a new PZT material that will be applied to these 2 domains, and then we'll rotate, we'll do a 180-degree polling direction change. Let me add that new material. And so now we have these 2 domains. So you have PZT material 1, and then PZT material 2. And this one is going to rotate it 180 degrees so that the Z direction's in the other direction. Now you can double check the orientation of this using Comsol. You can develop a plot group that shows the polling direction and can confirm for yourself that you have set these things up properly. So I'm not going to do that today for the sake of time, but you can generate these types of plots to confirm for yourself if you've set your model up correctly. I also wanted to point out that we are going to be using the stress charge form, as Kyle mentioned, but you could change that to the strain charge formulation if you have material properties for your PZT crystals that are in that form. Okay, we also need to constrain this, so I'm going to add a prescribed displacement boundary condition to bottom boundary here. And we're going to check this box here to constrain the Z displacement. We don't need to constrain the displacement in the R direction because the axisymmetry boundary does that for us. Okay, so those are the boundary conditions for solid mechanics. Now on to the electrostatics equations. Now in this case, we're only going to solve for the voltage, the potential within the PZT crystal. So again, I'm going to clear out the selection list, and then I'm going to zoom in here and only add in these 4 domains. I'm going to add the ground boundary condition to there, there, and there. And then I'm going to add in the electric potential, will be the driving voltage on these 2 boundaries. And we'll set the electric potential equal to 50. Okay, so we have our ground here on these boundaries, and then we have our electric potential here. We do need to specify material properties. I'm going to add in a few material properties from the library here. First one is going to be aluminum. By default, that's added to all domains, and we'll override that here in a second. There are a number of, Comsol provides a number of specific piezoelectric properties for different materials, from aluminum nitride all the way down here to zinc sulfide. But you can also add in your own if you wish. There's also a number of different flavors of lead, zirconate, titanate. Now, I've modified one of these to add in some thermal properties. You can see I added this little tag with thermal, and I uploaded that to a user-defined library. So I'm going to add this to the materials list here. And so this is the same as what Comsol provides, but the thermal conductivity and heat capacity, because remember, we're also going to solve the thermal aspect of this problem. And then finally, I'm going to add in a titanium material from the built-in section. Okay, so the PZT crystals are lead, zirconate, titanate, and I'm going to add those to the selection list here for the PZT. And then for titanium, it's going to be the top two domains up here. And then aluminum will be everywhere else. Okay, so the first thing that we're going to solve this problem using a couple different studies. And the first one is going to be this eigenfrequency analysis. So let's go ahead and compute. It's going to search for the resonant frequency of the coupled electromechanics and electrostatics equations. It should take just a few seconds to solve here. And you can see we get a graphic of the mode shape of the first resonant mode here. If you change this drop-down list, you can see another graphic of some of the other different mode shapes at the higher frequencies that we solve for. You can also generate a 3D view of this. So we solved in 2D, but Comsol will revolve that for you so you can get a better visualization of the real three-dimensional system. You can also animate this. Using a player, and you can see doing a dynamic data extension here, you could see a visualization of how this is going to vibrate. Now these are scaled in terms of the magnitude of the displacement here. It gives you some idea of the vibrational frequency, the resonant mode that we solved for there. That's the first one. You could come and examine maybe one of these higher order ones or higher frequency mode shapes. Now, I did want to emphasize that this is the coupled PZT resonant frequency that we solve for. So this is more than just a solid mechanics solution. This is actually the fully coupled problem. So that's one of the higher order modes there. Now, you can solve the uncoupled problem as well. Well, we're not going to do that, but it is different by a few hertz. And so it's nice that Comsol is able to handle that for us. I did want to also just show, you can look at, this is now a plot of electric potential within the PZT crystals, and you can visualize this, again, using the dynamic data extension and see how that's going to move across phase. Okay, so now we're going to add in the thermal aspect to this problem and right-click on component node here. I'm going to add physics. I'm going to bring in heat transfer in solids. And then we'll need to set up the coupling and make a few more changes here. So for mentioned, we're going to have a heat flux boundary condition on all boundaries. Effective heat flux to air. Put a value of 5 here. We're also going to add in the heat source. So this heat source is going to come in to all domains except the PZT crystals, actually. So we're going to neglect any of the structural damping within the PZT crystals. But the damping term here is going to come in through the aluminum and the titanium that are vibrating. So we're going to add in the structural damping. Give it a damping type, the isotropic loss factor. And that's going to read from the material, and then Comsol very nicely gives you access to a little warning. Hey, I need that damping term now. So if you tried to solve, it would warn you at that time, but you can also notice the red X. So you do need to enter in the loss factors here. I'm going to give aluminum a value of 0.001. I'm going to give titanium a value of 0.006. And then I'm going to add a new study here to be able to solve in the time domain. Now this study, we're going to first solve for, we're going to solve this in the heat transfer and solids equation. So I'm going to toggle off solid mechanics and electrostatics and the PZT effect. But I do need to solve in the frequency domain, or and decide on a frequency to drive this at. So we're going to solve at that first mode. This is the frequency that we solve for. Don't solve heat transfer in the frequency domain. I'll turn these off. And then we'll solve for a time range of increments of 20 seconds up to 10 minutes. This should solve here in about, did everything right, this should solve here in about 20 seconds. And I could show you the temperature rise as a function of time as this device is driven with this particular resonant frequency. Now, this particular model doesn't have the full intimate coupling with the thermal expansion effect, but you can add that in relatively simply, and we have done that for our customers in the past and shown that when you add in that intimate coupling, that there can be scenarios where the shape change from the PZT, the expansion from thermal expansion, can cause a different resonant frequency of the devices, in addition to the temperature-dependent properties have an effect. So I'm not modeling that in this example, but we do still get a thermal effect here that at times 600 seconds, 10 minutes, we've heated the tip of our device here about 50 degrees Celsius or so. And also generate a animation of this in time. And once this comes through, then I'm going to pass it back to Kyle. He's going to wrap up a few more things for you. So thank you.
Great. Thank you, Josh, for another excellent demonstration of using Comsol to solve this type of problem. Now, before I hand this back to Comsol, I wanted to just briefly introduce you to who we are and what we do at Altasim. We're a company that believes strongly in helping people obtain benefits from computational modeling. We do this in several ways, but we always do it in a way that enables our customer to be as independent from Altasim as they want to be. We develop computational models as part of our consulting services, and we'll provide those models to our clients so they can run additional cases. For clients that are not familiar with using Comsol, we provide training from beginner to advanced classes. Finally, for clients that seek to solve additional cases without the knowledge of using the full Comsol multiphysics package, we do develop simulation apps for special use cases. And we do this across a very wide range of physics and industries. I hope that by watching this part of the demonstration of how Altasim developed this complex multiphysics model for our clients, you've learned more about using the software for actual product development cases. Hopefully the case study that we showed today of a fairly complex problem of the heating of a vibrating structure driven by a piezoelectric transducer was helpful to you and that this example demonstrated one of the many ways that Altasim has been able to support the technology development of our clients by developing models using Comsol multiphysics. Also, hopefully you have a better understanding of the benefits of computational modeling and the support of Altasim. And with that, I would like to hand it back to Comsol. And Chandan, you.
Thank you, Kyle and Josh, for the great demonstration and presentation. Now let's have a look at some of the unique benefits to simulation and piezoelectric modeling in the Comsol environment. Comsol, as some of you might know, is a multi-physics as well as single physics simulation platform. It covers mechanical, fluid, electrical, and chemical simulations, or really any physics that you can think of. Comsol is particularly well known for multi-physics or coupled phenomena. You can use the built-in physics interfaces available with Comsol or define your own custom physics. You can model and combine, for example, electromagnetics, heat transfer, chemical reactions, fluid flow, and structural mechanics to enable complex simulations of multi-physics phenomena such as Joule heating and thermal expansion like we just saw, convective cooling, fluid structure interaction, acoustics, and so on. You'll also find that Comsol software provides not only the capability to set up your model and run multiphysics simulations, but also to design computational simulation apps based on your model, which have custom user interfaces. This interface, called the Application Builder, is one of the major innovations of Comsol multiphysics. The Application Builder is a tool that lets you turn your sophisticated model into an easy-to-use app that your colleagues and customers who are not into modeling can use. This enables them to contribute to the analysis process. Now let's talk a little bit about piezoelectric devices modeling in Comsol. Piezoelectric devices modeling requires modeling of both detailed electrical and structural behavior of piezoelectric devices. The MEMS module in Comsol offers the electric currents, electrostatics, and electrical circuit interfaces to model detailed electrical behavior and electrical elements in your model. At the same time, the piezoelectric devices interface in Comsol that we just saw in the live demo allows you to model the structural behavior of your device. The automated multiphysics coupling ensures that your model incorporates all the electrical and mechanical aspects in a bi-directionally coupled way. For instance, you may want to have a finite element model of your piezoelectric device, but at the same time, you would like to use a lumped elements approach for modeling the electrical circuitry that goes with the device. This type of coupling between the finite element model and the electrical circuit is also possible to do in Comsol multiphysics. The piezoelectric devices interface in Comsol presents fully coupled piezoelectric equations, some of which we saw in the beginning of this presentation. You can model both direct and inverse effects using the same interface, as Kyle mentioned early on. Also inbuilt are both strain charge and stress charge formulations, depending on what properties you may have access to. The interface also allows you to combine piezoelectric materials with decoupled isotropic and anisotropic structure and electrical materials, like we just saw in the presentation. Furthermore, you can even couple your piezoelectric devices with acoustics to study devices such as transducers. In terms of the type of analysis, the piezoelectric device interface supports static, that is steady state, modal, frequency response analysis, time-dependent analysis, and perturbation analysis. Perturbation analysis are those that consist of, say, a DC bias signal and then a harmonic AC perturbation on top of the bias signal. Now, one of the most important aspects of piezoelectric modeling is specifying the material orientation. Depending on the crystal cut or orientation of the material, you can define a local coordinate system by specifying the Euler angles that represent the material orientation. You can then use this local coordinate system within the piezoelectric devices interface for specifying the material orientation. This can be combined together with other materials which may have a different orientation defined by another coordinate system. Now here we are seeing some examples of piezoelectric modeling taken from our applications gallery. On the top left, we have a simulation of AT-cut quartz oscillator that studies the mechanical response associated with the thickness shear vibration due to a series capacitor. Another model shows the case of a piezoelectric valve, which consists of a seal pushed by a stacked piezoelectric actuator to close or open the valve. The Tonpil transducer model is an acoustics piezoelectric interaction model consisting of piezoceramic rings stacked between an aluminum head and a steel mass connected by a steel bolt. The model studies frequency response of the transducer in terms of transducer characteristics such as specific acoustic impedance, transmitting voltage response, directivity index, and far field calculations. The figures on the right show examples of modeling a surface acoustic wave device and a bulk acoustic wave device to study their frequency response for the desired resonance modes. Some typical analysis results for piezoelectric devices are shown on this slide. These analyses may consist of, let's say, computing the desired mode shape, like we just saw in the live demonstration by using the eigenvalue solver, and the resonance frequencies, or computing the induced voltage in the piezoelectric devices, such as energy harvesters, or maybe computing the admittance of a transducer for a range of frequencies around your resonance frequency, or perhaps identifying different wave modes and computing the time of flight of different wave modes excited in a time-dependent transducer simulation. Now, all of these different types of computation, ranging from steady-state, modal, frequency response, time-dependent, pre-stressed analysis, or a perturbation type of analysis, they're all possible using the same piezoelectric devices interface, but using a different analysis type. Now with that, let's move on to the question and answer section of this presentation. Over to you, Dexter.
Great. Thank you, Chandan. Let me just put out this product suite slide for everyone to see. I also would like to inform everyone that the presentation, the PDF that was in the resource page, has been updated. The one for today is now up there. What you should do is refresh your browser, and you'll see today's PDF presentation for you to download. Let me go to some questions that I think are probably best suited for Kyle or Josh. And the first one I have here is, are the loss factors for aluminum and titanium published somewhere?
Yeah, we did get those out of the literature. I don't have a reference immediately, but they are available in the literature.
Okay. Let's move along. Do the piezoelectric coefficients of the materials change under vibration compared to the static state? And is that implemented in the model?
Boy, that's a good question. Is it implemented in the model? I'll take the second half of the question first. No, it is not implemented in the model. And
okay.
Do they actually change under vibration? They very well might. Somewhat depends on the material itself. But it usually would be considered a second-order effect in most typical piezoelectric materials.
Okay. The list is changing here, so let's hope that this is a good question for you, for Kyle. There are two steps in the study: a frequency domain step and time-dependent step. Is the time-dependent step basically solving for the heat generated if the device is run at 11 kilohertz mode for 10 minutes without actually solving for electromechanics for 10 minutes?
So, an excellent question. So the way that this works is that you develop the heat source in the frequency domain, and then you apply that heat source in the time domain. And then the heat source is effective for as long as you run the analysis.
Okay. Shannon, let's turn back to you. Have a question here. Can you show us the energy harvesting example using piezo and where you apply an external force and generate a voltage across the piezo material?
Well, I cannot show an example right away right now. If Jason, you could reach out to us, we can certainly send you such an example. But to mention modeling the energy harvesting type of effect is possible using the very same interface, the same analysis type, except that your boundary conditions will be different. You're not going to be applying a voltage. You're applying a load, and you will have another boundary condition, a terminal boundary condition, to measure the induced voltage. So yes, it is possible to model using the same interface, and just do get in touch with us after this presentation so that we can send you some example like that.
Okay, and Chen, as long as we have you here, let me ask you another one here. If I have a 2D model that cannot be resolved to represent the real 3D model, can I see the results of mode shape in 3D, specifying the deep, for example, in a specific axis?
Yeah, good question. So if the results of the 2D model are assumed to be invariant in the third axis, which is not drawn, then yes, you can. All you got to do is first model your problem in 2D, and then draw out the third dimension as in the 3D geometry, and just map the results from your 2D simulation to the 3D geometry. So the only step that you would have to do here is draw the three-dimensional geometry as well by extruding the 2D cross-section that you have already drawn. Mapping would be done by using Comsol's one of Comsol's coupling operators. It's called general extrusion, which is used for mapping from one geometry to another. Okay.
Kyle and I guess Josh too. Are there other examples of how heating affects vibration of piezoelectric materials?
Yeah, there are. And one of those examples would be the one that Chandan was talking about earlier with the energy harvesters. And there are a variety of examples, and they're even in the model library. So if you go up into the model library and look for heat generating in a vibrating structure, that's a very good example in the library. I think that would probably be the best one if somebody wanted to try that out initially. I think that would be the best place to go.
Another question for you. How would you verify and validate this type of analysis?
Yes, verification and validation are challenging, particularly in multiphysics problems. One of the things I would say is that, and we didn't really show this in detail, but breaking down the physics and solving physics independently and, trying to do some experimentation that would confirm things like natural frequencies, those types of things would be a very good way to go. When you're talking about the transducers themselves, there's a lot of great papers that have been published on specific transducers, so you could break the problem down just simply into the transducer, run that analysis, compare it back to the literature results, and then you could at least validate the transducer part of the model, because that's a key part of the model to make sure you've got the transducer set up correctly. So I think that would be the things I would say is break the problem down into its subcomponents, try and validate those subcomponents, and then then you put the whole system together, you analyze it, and then ultimately you're going to build a physical prototype to test it. The virtual prototyping doesn't completely eliminate the need for physical prototypes. It just hopefully gets you to a solution that's dead on in the very first prototype. But if not, you'll see the effects that of modeling simplifications in your physical prototype.
Okay, great. Another question here. What would happen to the analysis you showed if the piezoelectric material was constrained from thermal expansion?
Yes, and so we kind of alluded to some of that in the presentation, where we talked about the fact that, if you've got a thermally expanding material and you constrain it so it can't thermally expand, you're going to generate thermal stresses. And those thermal stresses come directly back into the constitutive equation. So they become another stress that's applied, which is then going to change the electrical response and the resonant frequency of the transducer. And so, those are important aspects of the problem, to be able to constrain that PZT stack in a way that's consistent with what's actually going to happen in a physical condition.
Okay, I think maybe one more question for you, Colin. I think we'll turn back to Shannon for one or two. What is the most challenging aspect of modeling problems with piezoelectric materials?
Well, there are a lot of them, but I think probably what comes to the top of the list is it's the correct coupling setup between the electrostatics and the solid mechanics. The electrostatics is, at least in a lot of these problems, is pretty simple. You typically have some kind of voltage applied, and this solid mechanics can be fairly simple as well. But the coupling between the two can be a challenge, particularly in the proper setup of the poling directions, which is why we talked about it, Chandan talked about it, setting up those poling directions and applying the consistent electrical boundary conditions at the surfaces of the piezoelectric stack. I think that's what, in our experience, that's where we tend to make mistakes. We don't get that set up properly, and then we're scratching our heads and debugging for a little while. So hopefully that helps, so you guys don't make that same mistake.
Okay, let me just, there was another question that came in earlier, and I think it might be along these lines. The question was, is the polling direction plot that was just shown a new feature to the 5.3a, or was that introduced previously?
No, that has been around for a while. It's kind of buried in with the plotting, but it is something that's been available for a while.
Okay. Great. Thanks, Carl. So, Shannon, I have a question here for you. The difference between using the electromechanics interface versus the piezoelectric interface for using for the purpose of modeling piezo MEMS, what are the advantages and disadvantages associated with each interface, I guess, for modeling piezo MEMS?
Yeah, this question used to come up often in the earlier versions of Comsol because of the restriction in the electromechanics interface to not be able to model a piezoelectric device. Electromechanics interface consists basically of, let's say, electrostatically actuated structures, which is, well, you could say a piezoelectric material as well. But it does a little bit more. That is, it also evaluates the electromagnetic field around your vibrating structure, which is something that you don't do when you normally model a piezoelectric device. You make some assumptions, so you're not doing electromagnetic calculations around the vibrating piezoelectric material. With electromechanics interface, you can do that now, and you can also model piezoelectric materials within the electromechanics interface with version 5.3a. This is something which was not possible to do in earlier versions, so that is a huge step in the electromechanics interface.
Okay, Jen, I have one other question, but I think that might be best answered by some of the slides that you're about to present. And the question was, how can we get the Comsol software? But I know you have some slides that may help answer that.
I do. They're at the very end here. So there is the link here, Comsol.com product download. That's where you would go to download the software, but you probably might have already been contacted by a Comsol representative. So if you request for a trial or request a demo, you can go there. If you haven't been contacted, that is, and then request a trial passcode to install the software from after downloading it.
Okay, great. And I think you had some other slides that you wanted to show that before that final
Yes,
slide.
I did. Well, this is our product suite, and we have several add-on products here that can be combined with Comsol Multiphysics core package, and these all can be combined with each other in a variety of areas which range from electrical, fluid, heat, mechanical, acoustics, and chemical simulations, as well as several multi-purpose modules and tools for interfacing with external software, such as CAD programs or software for data organization, visualization, so on. Here I've highlighted 3 of the modules: MEMS module, structural mechanics, and acoustics module that allow you to model piezoelectric devices. The MEMS module has additional electrical capabilities that may be needed in such modeling. I also want to remind our listeners that we do have an event called, one-day event called Comsol Days at various locations throughout the United States. Here you can come for a day and attend some mini training courses in a variety of areas and also interact with your Comsol representative and with technical support and application engineers. And every year we also have a Comsol conference. This year we have it on October 3rd in U.S. here in Boston. We have that annually throughout at the various locations that are listed on our website. Now, this is a great place to attend, again, a variety of training courses where you can meet the developers and also application engineers, and again, interact with other people working in the same areas in industry and universities or doing research. So that's a great place to learn and meet people who do similar kind of analysis as you. So this would be a 3-day, I think it's a 3-day event. And then for any further questions that you may have, technical or license related, please do get in touch with us. We have listed some of these links here to get in touch with us. And you will find more resources about learning more about Comsol and how to use it for your particular simulation on our website, which contains several sold examples and documentation. However, please feel free to reach out to us with your questions to know what examples would be more relevant to you if you are new to Comsol.
Okay, great. Thank you, Chandan. I want to be sure to get this last slide out. This is the PDH certificate code, continuing education credit. This is the code. This will be part of the archived webinar as well. So just want to get that out there. We are out of time, and as I indicated earlier, this session will be archived in about 24 hours, and once the archived webinar is available, a notification email will be sent to all the registrants. I'd like to thank our presenters from Comsol and AltaSim for making this such an informative hour, and our sponsor. And thank you, our audience, for participating in today's session, and we hope you found today's event valuable, and we'll return for your future IEEE Spectrum webcasts. Thank you.